Hello, researchers. I am Nick Sibaan, a faculty member of the Mathematics Department under the College of Numeracy and Applied Sciences. In this presentation, I'm going to share to you some of the commonly used basic quantitative research designs. This presentation is example-based. Majority of the examples used in this presentation are related to topics in education or in social sciences in general. Let us begin. Again, in simplest term, a research design is just a blueprint or a skeleton for research. Let us recall our research process. Where is the identification of the research design? It's there. And we see that it comes before data collection, data analysis, any of this. The stage where we answer the problem based on the data gathered. The research design comes way before those things. And to clearly understand what we mean by a research design, let us use an example. I'm going to make use of the process of how we build our buildings or houses. So research design is analogous to a building blueprint. The blueprint will guide the carpenters or the workers during the actual process of building. The blueprint also specifies not only how the house would look like, but also the materials that are to be used, how big. It even estimates the cost of the house. Like a building blueprint, the research design plans ahead of time important research elements such as the population and locale, the procedures that are to be done, the instrument that are to be used, the statistical tests that will be helpful in analyzing the data, so that research designs actually ensure that actions achieve the objectives. And more importantly, it is a way to avoid wasteful expenditure of your money, your time, and energy. Imagine reconducting the entire data collection process just because you did not plan your instrument. You realized that the type of data gathered by the specific tool that you used will not help you achieve the objective of the study. Let us differentiate research designs from research methods. Research designs are actually the overall structure of the research. Mas general itong research designs. It covers a lot of things, as we mentioned kanina. The population in locale, if you're going to sample, how are you going to do it, how large the sample would be, what tool is appropriate for your research until the statistical tests that will be used. For research methods, we are normally pertaining only to the procedures that will be used to collect and analyze your data. From this table, we see that research method is just a part of your research design. For this presentation, we're going to talk about quantitative research designs. Because there are other research designs, we have our qualitative designs and our mixed method designs. For quantitative research designs, these are of course appropriate for researches that are quantitative. What again are quantitative researches? These are researches that normally measures constructs or variables. It also explores the relationship between and among these variables. I'm going to show to you now the summary, the overall designs that will be discussed in this presentation. I am categorizing the quantitative research designs into two. One, they are the experimental designs, the other, non-experimental designs. And under the experimental designs are subtypes. The first one are called the pre-experimental designs. The second one, quasi-experimental designs. We also have the true experimental designs. And then under each subtype are the specific designs, which will be discussed throughout the remainder of this presentation. Under pre-experimental designs, we're going to discuss three. For designs under the quasi-experimental designs, and another 4 under the true experimental designs. For the non-experimental designs, these are our descriptive designs, can be categorized further according to purpose, survey, and correlational. And then according to time, if we're going to categorize the descriptive non-experimental designs according to time, we have our cross-sectional designs, longitudinal designs, and the retrospective designs. Let us start with our experimental designs. In the first place, what are experiments? According to Zimny, 1961, in an experiment, we objectively observe a phenomena which are made to occur in strictly controlled situations. Emphasis on the phrase strictly controlled situation. To clearly illustrate what we mean by an experiment, we have diagrams here to help us. So normally in an experiment, what we are actually interested of is establishing whether there is a causal relationship between two variables. Specifically, the two variables are called independent and the dependent variable. Dependent variable meaning the outcome variable. The independent variable is the variable that we manipulate. So in an experiment, we actually try to manipulate the independent variable. So if we do manipulate this one, we would expect changes in the values of the dependent variable. If that happens, if the dependent variable changes as we change or manipulate the independent variable, then perhaps, or most probably, there is a causal relationship between the two variables. In an experiment, we have to be cautious of another variable, an outside variable called an extraneous variable. These are actually variables that are not studied in the experiment but may influence the dependent variable. In an experiment, these variables must be controlled. So this is what we mean by controlling the situation. Confounding variables are just a special type of extraneous variables. So it does not influence only the dependent variable, but also the independent variable. Let us provide an example, a very simple example of an experiment. My independent variable here is the presence or absence of a teaching intervention. So in this experiment, we want to know whether using technology in teaching improves the performance of our students. So I'm going to manipulate this independent variable. Perhaps for some students, they will not receive this technology. For other students, they will be exposed to this technology, and then we compare their performance if there's a difference of if we can see evidences that this is indeed an effective intervention. Another example of an experiment, I'm going to know whether there is a causal relationship between the amount of review time that I provide my students before I start the new lesson to their academic performance. So I'm going to vary the amount of review time that I give to my students. Some would receive lower or shorter review time, and then others would have longer review times, and then compare their academic performance. In this particular experiment, there are extraneous variables identified. For example, IQ and level of anxiety. Since I have already identified them as my extraneous variables, then I have to control for these things. Let's provide another example. I have here as my independent variable type of fertilizer, and the dependent variable is yield in kilograms. So which type of fertilizer is most effective? And the extraneous variable identified here, there are two: soil composition and access to light. So to make this experiment controlled, from the effects of an extraneous variable, I have to make sure that in all plots that I'm going to plant whatever that produce is, I'm going to make sure that the soil composition is similar to all plots. And also, all plots receive equal amount of light. Where can we conduct experiments? We could conduct them in the fields, meaning in real life setting. The advantage of conducting your experiment in the field is that whatever results you would gather from your research, that is probably reliable because you actually gathered that from the real thing. And a disadvantage of doing that, of conducting your experiment in the field, is that there are a lot of outside variables, extraneous variables, or confounding variables that you need to control. And sometimes that is really difficult for a researcher. Experiments could also be done in laboratories. I believe we know what a laboratory is. The advantage of conducting your experiment in laboratories is actually the disadvantage of the other one. So, since you are doing it in an artificial environment, you are able to control for extraneous variables because you're just in a closed building or something like that. The disadvantage, though, is the reliability of the results because the results gathered from, or the results from a laboratory experiment might not represent what actually happened. So there's a chance that it's not exactly what happens in real life. Now, we mentioned a while back that independent variables are manipulated. These are the ways how we manipulate the independent variable. The first one is presence or absence technique. This is illustrated here. So one group is not exposed to the treatment or to the dependent variable. The other one is exposed. Another way is to vary the amount of technique. Just like our example a while back, the amount of review time, one class perhaps will be given 2 minutes for their review time. Another class will have more, let's say 4 minutes, and then another will have even more, 7 minutes. That's an example of manipulating the independent variable using this technique. The last is to vary the type, not just the amount, but the type. For example, you're going to identify the causal relationship between type of instruction to academic performance. You actually included 3 types of instructions. Another concept in experimental researches, we have what we call comparison groups. There are normally 2 comparison groups, control and experimental groups. The control group, that's the group that does not receive or they are not exposed. They are not exposed in the treatment or intervention. The experimental group, those are the group. I said those because experimental group could be more than one. There could be more than one experimental groups. These are the groups that receive the treatment or receive the intervention, undergoes the intervention. Another term, non-equivalent groups. It's pertaining to our comparison group. So comparison group is the general terms. These are the specific types of these groups. 2 groups are said to be non-equivalent if they are not similar in the characteristic that we are measuring. So suppose we have 2 groups. The other group is composed of students who are high performing because they have higher IQs, compared to another group composed of majority of the students in the other group, group B, have a lower IQ, struggling students. That is an illustration of non-equivalent groups. They are not similar in terms of IQ or performance. Non-equivalent groups. Random assignment versus random sampling. This will be used many times in this presentation, so we have to understand these terms. random sampling is actually referring to the process of selecting your sample from your population. So you identify your population, you identify your sample size, you now identify those subjects or people that will be included in your sample. That is random sampling, population to sample. And the manner of selecting those who will be included in your sample is random. Random assignment is pertaining to the distribution of your sample to your comparison group. It used here the term treatment group, but this is just the same with your experimental group. Random assignment means randomly assigning whoever is included in your sample to your comparison group. So the simplest illustration there, if you have one control group and one experimental group, then you have to distribute all those people in your sample to each of the comparison group. Well, it is possible that there are two experimental groups, so there are three comparison groups now. Then you have to distribute your sample randomly to the three comparison groups. Internal validity, this is also very important, a very important concept. This is the extent to which you can be confident that a cause and effect relationship established in a study cannot be explained by other factors. Remember that in an experiment, we are actually manipulating the independent variable to see if it has it causes the change in the dependent variable. But we also mentioned that sometimes outside variables such as confounding variables may influence these variables, especially the dependent variable. So if that happens, if we are not able to control our confounding variables, so both of our confounding variables is causing changes in our dependent variables, then in the end, we cannot really say why is the dependent variable changing. Is it due to the manipulation of the independent variable, or because it's influenced by a confounding or an extraneous variable? If that happens, then the experiment, the research in itself, has a low internal validity. To make the internal validity of an experiment high, we have to provide techniques, ways on how we control our confounding variables, no matter how difficult that process could be. As mentioned a while back, to achieve high internal validity, we should be able to establish that the effects of extraneous or confounding variables are controlled. But what are the techniques on doing that? That's what we're going to present next. Actually, the first one is what we mentioned a while back as random assignment. This is in fact the most powerful technique for equating groups so that the groups are not non-equivalent, so that they are equivalent. Random assignment is done by randomly assigning your sample to each of your comparison group. Another technique is called matching. Just to illustrate, we use again this example. We have our independent variable as the type of teaching strategy, and then academic performance as our dependent variable. Our extraneous variables are your student's IQ and the level of anxiety. Now, how do we do matching with this particular example? So from your sample, we always start from your sample. Because there are three comparison groups, we're going to select three individuals from your sample with about the same IQ and about the same level of anxiety. That means that you already measured the IQ and the level of anxiety of your students. And then from these three individuals, we're going to randomly assign them to your comparison group. So one would be randomly assigned to your control group and the other two with your two experimental groups. And then you do the process until all of your samples, your subjects included here, are randomly assigned to one of the comparison groups. That's how we do matching. The purpose of doing that is to make sure that your comparison groups are equivalent. We are avoiding non-equivalent in an experimental study as much as possible. Why are we doing that again? Because we want our experiment to have high internal validity. That's matching. That's the second technique, second from random assignment. Another technique, that's holding your extraneous variable constant. Let's provide again an example to illustrate. Our independent variable in this example is type of physical education program undergone. So there are two types of physical education program under. We have new or traditional program. We want to explore its causal relationship to our dependent variable strength. Which program results to a better strength, perhaps among athletes? The identified extraneous variable here is sex. Now, to control for the effect of this extraneous variable, we can make it constant. So instead of involving female and male people in your experiment, we can actually consider females only or males only. From the sample, we stratify first. We select females only, and then randomly assign these female individuals to our comparison groups, the traditional physical program and the new physical education program. That's holding your extraneous variables constant. Another technique, we build the extraneous variable into our research design, meaning if that's our original paradigm, so sex is our extraneous variable, you integrate it really to your research design and become one of the independent variable. Just to illustrate what we mean by integrating it in our research design with this example. So for female participants, they were randomly assigned to the two programs. It was done the same for the group of male participants. Here is another technique. It's called analysis of covariance. This is very statistical, a statistical technique done when initially in the first stage of the experiment, your comparison groups are non-equivalent. They have dissimilar characteristic, perhaps an IQ or level of anxiety. And if that happens, this technique can be done. It statistically equate the two groups so that the effects of being a non-equivalent group is minimized. Counterbalancing is a specific technique used for repeated designs. We're going to talk more about this later on. Okay, so let's now start. Let's proceed to the different experimental designs. So under the experimental designs, there are three subtypes. The first one is our pre-experimental design, and then under it are the specific designs. So we will start with the one group post-test only design. Other authors would term this one as the one-shot case study. And from its name, it actually involves one group, and your intervention or your treatment is administered to them without a pre-test. So after providing them the intervention or giving them the intervention, the treatment, and then see whether there is an increase or decrease of what you are actually measuring. So that's it. From that sample that you selected from your population, you simply give them the intervention or the treatment and then perform a post-test or measure after the treatment is provided. I have an example here. My intervention is called learning algebra using software, and in my dependent variable is their academic performance, their algebra skills. Very simple. You just expose them to the intervention, which is the learning algebra using software. After that, they will answer an algebra test, a post-test. Another example, I have here a pill. This is my treatment, and we are trying to measure whether it helps build muscles. Another pre-experimental designs, we call it the one group pre-test post-test design. So ang nadagdag lang dito, it's the pre-test part. It's just the same with the previous design, but we are actually adding an element, the element of a pre-test. So you have one group of subjects or participants they answer a pretest, or you initially measure them, they are exposed to your experimental treatment. It could be an experimental treatment or an intervention for us in the education sector, and then you let them answer a post-test, or you measure it after being exposed to the experimental treatment. And then after that, you compare the scores from your pre-test and post-tests, or you compare the measurements from your initial and final measurements, and then see if there's an increase or decrease, or there's no change at all with the values. Yes, with our example a while back with the algebra performance, we simply add the element of a pretest. Or with our pill, before you give the pill, you first measure, and then after the exposure, after some time, you again measure the pre and post measurement. Now, we have a question here. Why is one group pretest post-test design superior over one group post-test only design? Because yes, the design involving the pretest is more superior. Well, obviously in this design, we have a baseline, a comparison group. Actually, there's only one group here, but at least we can compare something here. We know whether there's an increase or decrease or none at all with the construct or variable that we are measuring. The problem with this is we do not have an idea whether the intervention is the reason why we have that measurement, why we have that scores of students. In this design, at least we have an idea whether there is an increase or a decrease or an improvement with the muscles after being exposed to your treatment. So internal validity is higher here, is better than this. Because again, internal validity is making sure that's the extent of your confidence that what we are observing in the dependent variable, the changes in the dependent variable, is due to your treatment and not because of other factors. We have a third design under the pre-experimental designs. It's called the post-test only design with non-equivalent groups, otherwise called static group comparison. And although in this design it tried to use more than one comparison groups, because in the two previous designs it only used a single group of subjects. In this design we are using two, but they are not necessarily equivalent. They are non-equivalent groups. So you have two groups, you expose one group to, so actually we can think of this group as our control group, the other one is experimental, but the two groups are not necessarily equivalent. You just have two groups and then let them answer a post-test. There's no even, you haven't even integrated a post-test or initial measurement in this design. Yes, and then the scores here are compared. By using the same example and using this particular design, our experiment will look like this. One group of students, they're exposed to the treatment, to the intervention. Another is not exposed, and then both of them will answer a post-test. The scores will then be compared after. In this example, one group of people will be given the pill, another will be given a placebo, and then both of them will be measured. If this group perhaps have a better muscle development, then we say that that's due to perhaps the pill. But again, the problem with this design is you did not involve a pretest, an initial measure, and that the two groups in the initial stage of the experiment, they were not, you did not establish that the two groups are equivalent, and that's a threat to internal validity. If we compare the third design to the second design, we say that this is a better design though compared to this one, because in this design we actually introduced a control group, and doing that would improve our internal validity as mentioned. Let us now proceed to our true experimental designs. Why are these designs called true experimental designs? Because this design actually offers a high internal validity to our research results. And why is that so? It's because in these designs, we include control groups. So all of the designs that are under these true experimental designs have control groups. They involve a comparison group, a baseline group, and it always involves random assignment of participants. So you have your samples. The samples must be randomly assigned to one of the comparison groups. If your design have these two elements, then most probably that is a true experimental design. Let us now talk about the first one. It's called the pretest post-test control group design. So it has an element of having a control group. From the name itself, it also involves a pretest. Of course, in between, you expose your subject or participants with your intervention or your treatment, and then you measure it again. That's your post-test. So to illustrate, you start from your sample, you randomly assign your subjects to your experimental group or groups, because it could be extended to more than 2 comparison groups. You expose both of them to your treatment, and then you measure. That could be either through a post-test and then compare later on. As mentioned, this design can be extended to more than 2 comparison groups. For example, you could have 3 experimental groups because you have 3 treatments. And then, of course, most probably you will only have 1 control group. The group that will not be exposed or will be given the experimental treatment. All of these comparison groups will answer a post-test, and then the scores will be later on compared. Another design, this is our second design, post-test only control design. From the name of the design, it does not involve a pretest. So you only have post-test. You give your control and experimental groups the treatment, and then after that, you measure. You provide them a post-test. This is that design. So it's basically the first design minus the pretest. Randomly assign your sample, randomly assign their comparison groups. They answer a post-test, or you measure it after the exposure to the treatment, and then the scores or values are being compared. It could be extended again to more than 2 comparison groups. So you have more than 1 experimental group. They are all exposed to the treatment and then measured after. You will be the one to compare. The researcher will compare results from you. The third experimental designs, they are called factorial designs, and although this is applicable to social sciences, to social researches, this is more popular in the fields of agriculture and technical researches. What are factorial designs? These are designs from which 2 or more independent variables are studied simultaneously. In all the examples so far that we provided, we only have 1 independent variable, and we are exploring its causal relationship with or to an independent or to a dependent variable. So 1 independent variable to 1 dependent variable. But for factorial designs, you have more than 1 independent variable. Still, you have 1 dependent variable. That's how we can describe factorial designs in simplest term. You have more than 1 independent variable, you have 1 dependent variable, and you want to investigate the causal relationships simultaneously, not as 2 individual or 3 individual separate experiments. For example, I have 2 independent variables. The first variable is the method of instruction. There are 3 categories there. And then also, I want to know whether the level of anxiety affects mathematics performance or has an effect to mathematics performance. I have 2 independent variables. I do not really have to conduct 2 separate experimental studies because I have two independent variables. I can actually do that simultaneously. And the design appropriate for that is called the factorial design. This is more specifically termed as factorial design because there are two factors. If there are three independent variables here, then it's called a three-factor factorial design. If there are four, we call it a four-factor factorial design. The layouting could look like this, especially when we present our data. If we use this design and we are to present our data, it would look like this. It's actually like a multiplication table where one row or one column would represent one independent variable together with its categories. So in the columns, it shows us the type of instruction. There are three type of instruction involved here: computer assisted, lecture, and discussion. Anxiety is presented as a row. There are two categories, that's why there are only two rows, high and low. Anxiety is categorized as either high or low. Let me provide you an example, but this time in the agriculture department. There are two independent variables also. Type of fertilizer. So type of fertilizer could be organic, commercial, or mixed. Frequency of watering. Ilang beses natin dinidiligan yung pechay. Growth of pechay is our dependent variable here. Could be once a week, three times a week, and every day. And simultaneously, we want to explore the causal relationships of this. Which of the fertilizers yield the best growth? And which frequency of watering yields the best growth of pechay? This is how we're going to lay it out. The best advantage, therefore, of a factorial design is its ability to explore causal relationships with more than one independent variable. Let us now talk about some of the elements of a factorial designs. So if you read a study using a factorial design, most probably you will encounter the following terminology. We have what we call the main effect. So the main effect, it's referring to the effect of one independent variable on the dependent variable. That's the direct effect. And then we also have what we call the interaction effect. That's the effect of one independent variable on the dependent variable depending on the level of another independent variable. Because the independent variable will interact, it is possible that there is an interaction between the two independent variables before it affects the dependent variable. Let's illustrate what we mean by these effects using our example. The relationship between the independent variables type of instruction and anxiety to academic performance. And at this time, the researcher was able to gather data. The results are summarized here. So under computer assisted with high anxiety, there were 10 students. Under lecture with high anxiety still, there were 15. Under discussion with high anxiety, there were 20. So there are 6 cells here. First, we investigate whether there is a main effect of anxiety on the level of math performance. And to answer this one, we look at the average of the values here, and that's the mean. 10 plus 15 plus 20 divided by 3 is 15. We do the same for the second row, and then we compare the two rows. Because we are investigating the effect of anxiety to our dependent variable. So obviously it is higher here, meaning the performance is higher for the group of students with low anxiety as compared to those with high anxiety. So although we do not base solely our judgment by observing this one, because we have to do a further statistical analysis here, just to illustrate to you what we mean by main effects. Obviously the performance here is higher than this. This is where we could see that there is a main effect of a particular independent variable. How about the main effect of the second independent variable? That's the instruction type. We also see that there are differences in the means. So 25 is the mean or the average of the values here. 20 is the average of these two values here. Also, this is the mean of these two values here. And they are not the same. Some group have higher result or performance here. For example, under discussion, we have 25 followed by lecture. Lastly, the computer assisted group. This is a case where there's a high chance that there is a main effect of this independent variable to our dependent variable. That's how we interpret main effects in a factorial design. How about the interaction? There is a graph here. Actually, what we really want to show here is that it's parallel. If we graph the three scores here, for low, 20, 25, and 30, we do the same for high. It's parallel. That's how we know, using a graph, that there is no interaction between these variables. But how do we interpret it without using the graph, but just merely using the scores here? If we look at the pairs of numbers here, for example, under computer assisted, the score here is 10 and 20. Actually, the gap is 10. And we see that low students with low anxiety have the higher score or higher performance. If we move to another group, we see that students with low anxiety has the better performance, and actually the gap is also 10. 25 minus 15 is 10. The case is the same here. Low anxiety students have the higher performance by 10 units from the other groups. So we observe consistency between all groups. This is because there's no interaction between the two independent variables. What if the data gathered from the same experiment looks like this? Can we conclude the same about the main effects and the interaction between the variables? For example, the main effect of anxiety to math performance, the answer is no. This is where we could say that there is no main effect, although there is a further test to verify whether there is actually no main effect. But based on the means that we see here is equal, they're equal. Most probably that there is no main effect of the independent variable anxiety to the math performance. The observation is the same. When we look at the other independent variable, all of the means here are mean. So most probably, or there's a high chance that even if we do a further statistical test, we will detect a weak to no main effect of this independent variable. How about the interaction? To explore the interaction, we have to look at the individual cells here inside the table. If we look at the first pair, under computer assisted type of instruction, students with high level of anxiety were actually the students who had better performance. There were lower performance here. They are the students with low anxiety, remember that. Under the lecture group, there's actually no difference. And under the discussion group, we see that the case is reversed. Students with low anxiety, they were the students with the better performance. So that depending on the type of instruction, the effect of anxiety to math performance also varies. Here, low anxiety means better performance. Here, there's actually no difference at all. But interestingly, for this group, the students with high anxiety were the students with better performance, and that is shocking. But perhaps with deeper analysis, we might point out why that happened. It could be a methodological error, or there's actually a reason for this to happen. Anyway, we are trying to illustrate what we mean by interaction between two independent variables. This is the graph. They're not already parallel, they were intersecting lines. Okay, let's have our example. Let's have another example. This time, it's between the fertilizer and frequency of watering to the growth of pechay. So this is our table. It has values now. Let's suppose that we are able to conduct the experiment and these are the data gathered. Let us answer the following questions. First, is there a main effect of frequency of watering on the pechay growth? We start with this independent variable. If we look at the means here, again, where are these values coming from? It's the mean or the average of the three values here. Same through with the second row and the third. We can see that there are differences in the growth of pechay. The growth is highest under this group if you water it every day, followed by 3 times a week, followed by once a week. So the amount of water is a factor for the growth of pechay. So there is a main effect of this independent variable to the pechay growth. How about the main effect of the type of fertilizer you apply on the pechay growth? Again, we detect differences in the means. So the pechay that consumed mixed fertilizer, they had the highest or the best growth, followed by commercial, and then lastly the organic fertilizer. So perhaps if we test this further, we would detect that there is a main effect. Is there an interaction between the two independent variables on the pechay? Let's look at the individual cells. Under organic, the measurements here are the same. Under commercial, it's different. It's highest in this cell. So every day, if you water it every day and you use a commercial fertilizer, it will give you the best yield. However, if you are using organic fertilizer, regardless of how you water it or the amount of water you put to it, then it seems that there's no differences at all. If you use mixed fertilizers, mix between a mixture of organic and commercial fertilizer, we can still see differences here. The yield or the growth is highest or best under this group. So we can still say that there is an interaction between the two independent variables, because depending on the type of fertilizer, the effect of the frequency of watering might vary. Actually, it doesn't vary here. It varies only for commercial mixed fertilizers. Another experimental design, this is actually the last one that will be discussed, the repeated measures. This is a design in which all participants participate in all experimental conditions. So actually for this particular experimental design, the same group of subjects or people, they are exposed to different experimental conditions. Well, technically you have more than 2 comparison groups, but the subjects that were used are just the same. And if you remember the technique counterbalancing, if you remember the technique that was mentioned a while back, counterbalancing, that is applicable to this particular design. Those are the 4 true experimental designs. Let us move on to the third subtype of our experimental designs. They're called the quasi-experimental design. The word quasi means false or not true. And it's because we are not able to satisfy the conditions for an experiment to be considered true. What are those conditions again? The random assignment and the presence of control group. So one of these conditions are not met. Let's discover that in this presentation. We'll start with why. Why are you forced even to use a quasi-experimental design? Because the demand of experimental research are not always met. For example, it is not possible to randomly assign participants to group. That's one important condition for it to be considered a true experimental design. If you are able to randomly assign your sample to your comparison groups, it's almost a true experimental design. It's just that you cannot do that, makes it already a quasi-experimental design. An experimental research design that doesn't provide for full control of potential confounding variables, primarily because it does not randomly assign participants to comparison groups. Yes, that's what we mean. For quasi-experimental designs, because the influence of all confounding variables, they're not really ruled out, it is difficult to reach a high level of internal validity. We mentioned this a while back. For quasi-experimental designs, these are actually some ways on how we can at least establish internal validity. We should do it that cause must co-vary with effects. Cause must precede effects. The first two conditions here are easier than the third one. The third one says that rival hypotheses or alternative explanations must be implausible. We must establish that. The first design under this quasi-experimental design is called non-equivalent comparison group design. Again, we are using the term non-equivalent. So what do we have here? We have still comparison groups, control groups, and we are not able to randomly assign our sample to these two groups, and that could be a reason why the two groups here are non-equivalent. What do we mean by non-equivalent? Again, these are groups that are not similar of some characteristics. So perhaps ang nalagay dito sa experimental group, they are students with higher IQs compared to your control group, and that's already a source of bias, a threat to internal validity. Anyway, for this design, we have the two groups here. They are given or exposed to the treatment, and then they are administered a post-test, or they are measured after they are exposed to the treatment. Non-equivalent comparison group designs. Interrupted time series design. This is a design in which a treatment condition is assessed by comparing the pattern of pre-test responses with the pattern of post-test responses obtained from a single group of participants. Again, emphasis on the single group of participants. So we have one group of participants. So not all quasi-experimental designs pala involves a control group. It could involve only one group of participants. However, in this particular design, that particular group, they are pre-tested several times. So perhaps time yan. The first day, i-measure mo yung kanilang siguro attitude, mood. The next day, you're going to do the same. You are going to measure their mood. Siguro your participants here are those people with mood imbalances, mood swings, topic in psychology perhaps. Another day, on the third day, you measure it again. Fourth day, fifth day. So you measured, according to this diagram, you are measuring your group of subjects, participants 5 times. They're exposed to a treatment, another program that would help them stabilize their mood, and then after that, you will measure them again in 5 consecutive days post-tests, and then you will compare if there is an improvement. This is an example of an interrupted time series design. This is just an example, but I think we were able to illustrate it already. Let me read the example. Let me illustrate the example. What we have here are 9th grade students who had low general point averages and were frequently absent from school. They were assigned to attend an experimental classroom for at least 1 period each day, each school day. The percentage of students, so what are we measuring here? It's the percentage of students who were on task, or students who were doing what they were told to do. What is the treatment? The teachers will make the positive, the environment more positive. Siguro walang nagagalit, everything. How they say words should be in a positive way, in a malumanay way, and then the percentage of the students who were doing their tasks was measured. So percentage to, so ilan, how many of them are doing their task, how many of them are not. This is a possible data from that. So we can say that there's an effect of the intervention if there is a discontinuity. We call this the discontinuity line of the scores So just after the intervention, there is obviously a discontinuity of the pattern here. It went high. The percentage of students doing the tasks is higher after the intervention. This is an illustration that that intervention is effective. If the graph does not look like this, so the graph is almost of the same level as with the result during the pretest, then of course we wouldn't conclude that the intervention is effective at all. Another quasi-experimental design, they are called the regression discontinuity design. This is a design that assesses the effect of a treatment condition by looking for a discontinuity in regression lines between individuals who score lower and higher than some predetermined cutoff score. So just to illustrate, what you're going to do is to rank your subjects. So you have in the initial stage of the experiment, you're going to rank your subjects. It could be based on a proficiency test, so that you would know who are performing better on and who are performing less. And then from that ranking, you will get perhaps the top 30% and the bottom 30%. You will exclude now those students, those participants whose scores are in between the top and bottom scorers. And then one of these groups, the top performing, they could be labeled as the experimental group or the control group. It's either way. Or the bottom group, they could be the experimental or the control. You choose one of these two groups and then expose to the treatment. So it's two-way. You could give it to the top group or you could give it to the bottom group. And how do we assess whether the treatment is effective? Let's consider the following diagrams illustration. This is a case where, so these are actually the bottom group, the low performing students. These are the high performing students. And if you look at the graph after the treatment, so in this case, I think it's the top performing groups that were given the treatment. It's just a straight line. That is not an indication that the treatment is effective at all, because the top performing students have a higher score, obviously, because you rank them. However, the gap of their scores are not enough to really say that the treatment boosted the performance of the treatment group. This is a case where we can perhaps say that the treatment is effective because there is again a discontinuity of the pattern here. We know that they are top performing, so they will be having higher score, but high enough to say that the intervention is effective. What if we make the low performing students the experimental group, not the control group? Then to say that there is an effect, still there should be a discontinuity of the score. So perhaps this group will have a higher performance, higher than this. So still there will be a discontinuity of the pattern that we see here. Other quasi designs not included in this presentation, perhaps it could be your reading assignment. We have what we call single case experimental designs. Specific types, we have the ABA design, we have the ABAB design, multiple baseline design, and the changing criterion design. Let us now compare the pre, quasi, and true experimental designs, the three subtypes of experimental designs. Which of them are considered weak and which of them are considered strong? And what is our basis of saying that it's a weak design and a strong design? So yes, if you recall the concept of internal validity, you are correct. The design that threatens the internal validity of the research or of the experiment, they are the ones considered weak. Where the internal validity is high, that is the design that are considered strong. So obviously, the pre-experimental designs that we discussed a while back, they are the weak experimental designs because the threat to internal validity is really high. And that is because the element of random assignment or involving a control group so that we can compare better, they are not actually present for pre-experimental designs. So why the heck are we even mentioning this one? so that when we design an experimental research, we avoid, as much as possible, we avoid pre-experimental designs. Strong experimental designs are the true experimental designs. Random assignment and control groups are present. Quasi-experimental designs are somewhere in between, not as strong as a true experimental design, but of course superior over the pre-experimental design, because some of the designs are at least involving the element of the control group. Components of an experimental method plan. These are the things that we need to be reminded of about what to include when we prepare a proposal that is experimental in nature. So number one, we have to identify or describe the participants, and more than that, we also describe the selection process of these participants as either random or non-random. How did you select your participants? Identify the techniques for controlling the extraneous variables. For example, you will mention there that you used matching as a way to control the effect of your confounding variable. Tell the number of participants in each group and systematic procedures for determining the size of each group. For experimental research, investigators use a power analysis to identify the appropriate sample size for each of the comparison groups. Also, in an experimental proposal, a research proposal, we also clearly identify our independent variable and the dependent variable. Remember that for independent variables, there could be two, especially for factorial designs. We also describe or provide a thorough discussion about the instrument or instruments involved in the study. We describe further by mentioning the number of items and the scales used in the instrument, how its reliability and validity is established. Thoroughly discuss the materials used for the experimental treatment, and a pilot test of these materials may also be discussed, as well as any training required to administer the materials in a standard way. Experimental procedures, do not forget to mention those. Identify the type of experimental design that is to be used in the study. The different designs were discussed earlier. We have to choose from those. Is it pre-experimental design, true, or quasi? However, again, pre-experimental design is a weak design. Identify what is being experimented in your research. Provide a diagram to illustrate the specific research design to be used. When we discuss the different designs, they are accompanied by the diagrams, so the diagrams may look like those diagrams. Threats to validity, we should identify potential threats to the internal validity and design them so that these threats will not likely arise or are minimized. Also, we identify the threats to external validity. These are threats to generalizability. They must also be identified, and designs created to minimize these threats should be mentioned also. The data procedure, this is an example. I'm going to show you how we discuss this procedure. So it's a step-by-step approach for the procedure in the experiment. Number one, administer measures of the dependent variable or a variable closely related with the dependent variable to the research participant. That's my first step. And then assign participants to match pair on the basis of their scores on the measures described in step number one. So based from their pretest, I'm going to match and then randomly assign them to our comparison groups, meaning experimental or control group, and then expose the experimental group to the experimental treatment. And of course, you will not do that for the control group. And then administer measure of the dependent variable, and then administer a post-test or final measurement. That's a measurement after the exposure to the treatment, and then compare the performance of the experimental and the control groups on the post-tests using tests of statistical significance. This is just an example of how we should discuss the procedure. Data analysis, these are quantitative designs, so we expect that there will be statistical analysis involved here. It could be descriptive statistics. Descriptive statistics includes your means, the computation of the measures of central tendency, variability such as standard deviation in ranges. It could also involve inferential statistical tests such as your analysis of variance, analysis of covariance, or multivariate analysis of variance. It could also involve graphs or tests of statistical significance such as t-tests. T-tests are still inferential statistics though. Confidence interval in effect size as indicators of practical significance of the findings. Again, I am showing you what to include in an experimental research proposal. So let's be reminded of these items 1 through 7. Let us now discuss the second design, our non-experimental designs. Before we talk in detail about the different non-experimental design, let us consider the following situations. Suppose I am a researcher and I want to know whether cigarette smoking causes lung cancer. And to do that, I'm going to set up an experiment. I'm going to select 50 newborn babies and assign them to my experimental and control group. The experimental group, consisting of 25 newborn babies, will smoke cigarettes, and then the rates of lung cancer in the two groups will be identified many years later. Well, obviously, this is a highly unethical research. So even if this is a description of a true experiment, the design is following one of the true experimental designs, the research becomes unethical. So what do we do now? Because it's highly unethical, we won't be able to conduct this experiment. Are we going to stop? Because the research is highly important, very important. The answer is no. We have to resort in another design. For example, a non-experimental design. Another scenario, I am a researcher. I want to explore how students' learning styles. Learning styles are either visual, auditory, or kinesthetic. How are these learning styles affecting their academic performance? I'm going to proceed by setting an experiment, and from my sample students, I'm going to randomly assign them to my experimental groups. I have 3 experimental groups and a control group. So I have 4 comparison groups here. 10 students will be assigned under the visual group, another 10 under the auditory group, 10 under the kinesthetic group, and 10 under the control group. And then I'm going to tell them that they're going to apply, I'm going to force them to apply the visual learning style, and then the rest will follow. So these 10 students will forcefully apply auditory learning style, then be forced to apply the kinesthetic learning style. Well, I am out of my mind, right? The researcher is out of his mind, because you cannot actually assign a specific learning style to a particular individual if that individual is by nature visual or auditory or kinesthetic. You cannot do actually anything about that. You cannot change it so that you'll be able to set up this kind of experiment. So you see, there are cases where random assignment of your sample to your comparison group is not really applicable. This is also another case, another reason why we resort to non-experimental designs. In summary, researches in which the independent variable is not manipulated and there is no random assignment to groups, it's a non-experimental research. The research does not have direct control of independent variables because their manifestation have already occurred, or because they are inherently not manipulable, as was illustrated a while back. The researcher can look back at what naturally happened in the past, or the researcher can move forward and observe what happens. Time. Manipulation of an independent variable and random assignment to groups are missing. Random assignment might be missing not because we want it that way, but because we are not able to, because it's impossible to do that. Non-experimental research cannot provide evidence for causality that is as strong as the evidence obtained from true experimental research. Again, for true experimental research, we need random assignment, the element of random assignment in the presence of a control group to really establish, because what we are trying is to remove all the threats of internal validity so that we can say that whatever happens to the dependent variable, that is due to the manipulation of the independent variable. Most social, scientific, and educational research problems do not lend themselves to experimentations. For experimental research designs that let us beware of the following fallacy: post hoc ergo propter hoc. In English, this means after this, therefore because of this. This is a reasoning, this is a fallacy that we should avoid, because A preceded B, or A came before B, A must have caused B. That is a fallacy. Let us continue by classifying our different non-experimental research designs. The first classification will be according to time. The first type or classification is called a cross-sectional research. These are researches where the data are collected at a single point in time. If it's in multiple or across a time interval, then it's called a longitudinal research. There are subtypes. Trend study is when independent samples are taken from a population over time and then the same questions are asked. A panel study or a prospective study is similar to that of a trend study, except that the individuals, the sample you are asking, are the same throughout the time interval or throughout the duration of the study, the data gathering duration. Cohort researches are those that follows a group of people over time. For example, you're going to follow a group of senior high school graduates. First, you're going to identify what programs will these students enter at the tertiary level. How many of them will enter a STEM program, and how many of them will enter a non-STEM program, and then ask them their experiences for the duration of their stay in the university. And then you also follow them after they graduate, how many of them actually graduate from the program, and how many of them gets employed after graduating the program. So that is a cohort, an example of a cohort study. You are following a single group of people and then measuring or identifying some variables there or experiences. Retrospective researches are researches that starts with the dependent variable and moves backward in time. Let me provide you an example of a retrospective research. Right now, I am concerned with the academic performance of students in mathematics. It's low, and I want to know some factors that might explain such low performance, and some of these variables could have happened in the past. For example, their experiences in or during their high school days, the curriculum they were exposed to, or how their teachers taught them. It could be also factors such as experiences with their families in the past, or other things that happened in the past. Because those independent variables happen in the past, and I am trying to establish whether it has some relationship with their current academic performance now. That is retrospective in nature. Another classification of our non-experimental research designs is according to purpose. The first one, it's called the survey design. And what is this? It provides a quantitative or numeric description of trends, attitudes, or opinions of a population by studying a sample of that a population. The survey is actually, by definition, that's when you gather your data from a sample. So you cannot actually survey a population, because when you do that, you are already doing a census, not a survey. From the sample results, researcher generalizes or makes claim about the population. That's according to Creswell. Another author said that Survey studies ask large numbers of people questions about their behaviors, attitudes, and opinions. Some survey merely describe what people say they think and do. So the definitions here are similar. Now, if we are to prepare a survey research proposal, what should be included in our survey method plan? This is again according to Creswell. Well, first, you have to describe the survey design. You review the purpose of the survey and the rationale for its selection for the proposed study. This discussion can identify the purpose of the survey research, indicate why a survey is the preferred type of data collection procedure for the study over the other ones, or describe why this is appropriate and not the experimental designs. Indicate whether it is cross-sectional or longitudinal or retrospective, and also specify the form of data collection. Is it self-administered? Are you going to make use of a questionnaire, an interview, and the likes? You should identify the population in sample, the size of the population, if size can be determined, identify the sampling design. Generally, we have our probability and non-probability sample designs. Under the probability design, most probably you will be selecting from one of the probability design, especially if the research is a quantitative survey. Non-probability sample designs are really for qualitative designs. Discuss the procedures for selecting the sample from the available lists. Indicate the number of people in the sample and procedures used to compute this number. For survey researches, use a sample formula available in many survey texts. Creswell has provided some examples here. Instrumentation, number one suggestion, it's to name your survey instrument. Discuss whether your instrument is a researcher-made, a modified one, or developed by someone else. Take note that to use an existing instrument, you have to describe the established validity and reliability of the scores obtained from the past use of the instrument. Also discuss whether scores resulting from the past use of the instrument demonstrates reliability. So validity and reliability. When you're going to make use of a modified instrument or a combination of instruments from different authors, remember that the original validity and reliability established for these instruments may not hold for the new instrument. So you have to establish it yourself, the validity and reliability. Yes, sample items. Describe your instrument. Are there sections? How many items? The scales and all. Also, you have to identify the variables in the study. Relate the variables to the specific questions or hypotheses on the instrument. For example, relate the variables, the research questions or hypotheses, and items on the survey instrument so that the reader can easily determine how the researcher will be used in the questionnaire items. Plan to include a table of discussion that cross-reference the variables, the questions or hypotheses, and specific survey items. Finally, in a survey research proposal, you're going to discuss there how you will analyze the data and how you're going to interpret them. Also, you have to mention that you'll be reporting non-response participants, how many of them returned your questionnaire. Since this is data analysis, you also mention the statistical tests that you will use. They could be descriptive, such as your mean, median, mode, standard deviation, and all. When you conduct a pilot study for checking of reliability, then you will be using statistical tools there. For example, Cronbach's Alpha or Kuder-Richardson 20, you have to specify those also. Inferential tests that will be needed should be provided in the plan. Let us now proceed to the last non-experimental design, our correlational research design. What is a correlational research? These are researches that focus on measuring two or more variables and then assessing their statistical relationship. Why do we conduct a correlational research over an experimental researches? I think we have presented this one when we discussed a non-experimental research designs. Actually, the idea is just the same. Number one, it is not believed that the statistical relationship is causal. It's a causal one, or not interested in causal relationships. That's one. The statistical relationship of interest is thought to be causal, but the researcher cannot manipulate. We provided an example of a case where the independent variable is not manipulable because it's impossible, impractical, or unethical. So these are examples of the correlational studies. Level of anxiety to academic performance. Height of father to height of son. By genetics, right? We would expect a relationship. Attitude towards mathematics, high school GWA, college entrance exam. There are 3 variables here, all being related to Math 21 grade. Well, we cannot manipulate attitude. We cannot also change their high school general weighted average because this has already happened. Even the college entrance exam score. Now, this is again an important concept for correlational research design. It says here that correlations do not infer causation. Let us try to illustrate or give reason to this one. So for example, we have 2 variables here that we are trying to correlate: happiness and exercising. Actually, with the previous examples we showed, it's supposed to be like this. It's a double-headed arrow because for correlations, we have what we call a directionality problem. And this is the first reason why correlations do not infer causation. What do we mean by directionality problem? We have this example, happiness and exercising. When you are happy, it is possible that that's the reason why you exercise. So, happiness causes exercising. It is also possible that for some people, it's the other way around. Because they are exercising, they become happy. So, you see, one can be the cause of each other. That's the directionality problem. Number one reason why correlations do not necessarily infer causation. Another reason is what we call the third variable problem. We are still talking about happiness and exercising. So this is the directionality problem. It is also possible that they are being correlated because later on we will be providing a statistics that describes how strong the correlation of these 2 variables. So suppose it's strong. It's not because one causes the other, but it's because both of them are being caused by a third variable. This variable is called as spurious variable. The reason why these 2 are being highly correlated because they are connected by a third variable. Now, for correlational research designs, the easiest way to illustrate our results is by a scatter plot. These are scatter plots. We have our Cartesian plane, our x and y axis, that's where we plot. So basically, these are points. These are ordered pairs. And what we want to illustrate here are the 3 possible scenarios when we are doing a correlational research. Either we would have a strong positive correlation as illustrated here. An example of that would be if the 2 variables being correlated are score in some happiness test. So it's basically measuring your happiness, and the other variable is frequency of exercising. The happier you are, or the higher your score is in that happiness test, meaning you are more happy, then the frequency of exercising is also high. People who are happier are the same people who exercise more frequent. So the more you have this, the more you also do the other variable, in vice versa. Those people who scored low in the happiness test, meaning they are not that happy, they're sad, they're actually the same people who exercise less frequent. Another possible result is to have a strong correlation, but it's negative. The only difference is actually the direction. So if you look at this pattern, it's linear, it's approaching a line, still approaching a line for negative correlations. However, the direction is reversed. An example of two variables that are negatively correlated are, let's have a score in some anxiety test. So it's measuring your anxiety. So the higher your score here, the more serious your anxiety problem is. This is your academic performance, perhaps measured using your general weighted average or some proficiency examination. So that the more serious your anxiety is, we would expect that if we're going to identify 1 point somewhere here, so that's representing someone who scored high, meaning who has a serious anxiety. If we look at the academic performance, it's actually low. If we identify a person scoring low in this anxiety test, it's that person with high academic performance. So this is a strong negative correlation. The third image here is an example of two variables that are not correlated at all. It's literally scattered. I have an example here. The first variable is a vegetable yield in Mountain Province, and then the other variable is number of crimes in Baguio City. So the two variables are entirely not related, so you would not really expect a strong correlation here.